Hi there. Okay, I'm reading because this is the second time that I try doing a video. In the first opportunity, this video length was 1 hour, and that is too long. But here in this video, I'm going to show you many topics. So as first, this is what I want to show you first, okay? So this is the syllabus for the IGCSE 0748, and these are the topics that you need to know before the IGCSE exams. Okay, so in this video I am going to talk about data representation and just number systems. Okay, I'm going to do another video for this one, that is text, sounds and images, and until here. So how many videos you are going to have? I expect that I'm going to use just one video for every single chapter. Chapter one is data representation, but I already told you that in this one, there are going to be two videos, okay? I'm going to try to make just one video for data transmission. That is the second chapter. This is the third chapter, hardware, but this is the hardest one. So I'm going to try to do this video shorter because this topic is so hard, okay? Hardware, then the next one is gonna be software. The next video is gonna be the internet and its uses. And the next video is going to be about automated and emerging technologies. And the other part, that is, this is the paper two that you are going to present, is about algorithm and design and problem solving. Okay, so let's start. I'm going to try doing this faster. So if you get lost in any part, pause the video, rewind the video, and see the video again. Okay, I'm going to try to be so clear for you. And obviously here I have a presentation for you. So data representation, and we are going to talk about number systems. Okay, so understanding how and why computers use binary to represent data. Okay, so to understand this, you know that the computers um, is built with electronic circuits. That means that the computers recognize these values, ones and zeros. This one means that is on or high voltage, and this means that is off or low voltage. Okay, so everything in the computer is electrical signals. Okay, now this is the reason the computer is, this is the language of the computers. Okay, so how the computers represent data in binary. So every single thing that you are using in your computer, doesn't matter that if you are using numbers, text, images or sounds, all those information must be converted to binary. So that is so important that you understand this. Okay, so what is this about? So let's suppose that you are going to just type a number. This number, before being processed, let's suppose that this is the CPU. Here is where all information is processed. So when you send a one here, this one is converted to binary, then is processed or store. Okay, the same with text, the same with images, and the same with sounds. Everything is converted to binary before processing information, before storing information, or even before transmitting information. Okay, always computer, always use binary for everything. Okie dokie. Now, but what happened with the text? when we are talking about the test, let's suppose the letter A, this letter that depends of the configuration that we are using or we are having in our computers. We use one of two. Let me see if this microphone is recording. Okay. We use one of two codifications. Possibly we use ASCII or possibly we use Unicode. So, what is the difference between those um conversions or codes? Okay, or coding. Okay, so ASCII we can use 128 characters or possibly 256 characters. Okay, for example, let me try showing you here. So I'm going to use ASCII, and here look at this. Okay, so if you notice here, we start from 00 to 255, but Mr. David told us 256. Yes, because you are going to use from 0 to 255. And here you have 256 numbers. Okay, so using this code is limited. Why limited? Because you have only 256 codes here. Now, let me show you the other one that is Unicode. Unicode characters. List of Unicode characters. This is bigger than ASCII. Okay? Look at. Look at. That is too much coding. Okay, so what is the difference between them? ASCII is shorter, Unicode is too long. Okay, so if you want to use one of those for space, saving space, saving, use ASCII because this one is longer. Okay, so why I'm explaining this? Because this is done when you are talking about text. Okay, so here I have an example. If you are using the letter A, the ASCII of the letter A is 65, and the computer, when the computer has the ASCII code of the information, the computer converts the ASCII code into binary. Okay, okie dokie. Now, here, this part is easier. Why? Because the computer uses the binary information or manage the binary information using something that is called the logic gates. Do you remember this? For example, this is the and, oh no, and, okay? So you are going to have binary information getting inside this gate, and obviously you are going to have a result here, okay? Okie dokie. And obviously, all this information that is processed by the computer is stored in the computer, permanent or temporarily. That depends of the use that you are doing. And this information is stored in something that is called registers. Okay, so inside the register is the information that you are using. Okay, and this is for performing, for saving information, or for performing operations. Okay, okie dokie. Let's continue with the next one. Okay, this one is easier, and I'm going to try to do this faster. And I know that you already know it and you already understood this. So we have the number systems, denary, binary, and hexadecimal. Okay. So denary, we have the numbers from 0 to 9. Binary, we have the numbers from 0 to 1. And hexadecimal numbers, we have the numbers from the 0 to 9 and the letters A to F. Okay, so remember this. I'm going to show you an example of how to convert a denary number to hexadecimal number, but getting the binary number first. Okay, so I'm going to try doing this fast. So let me do it like this. Our denary number, I'm going to use 375. Okay, so as first, we are going to convert this number to binary number. Okay, and always in IGCSE and in computing, we use always, you know that a binary number is represented by 4 bits. But from this moment on, all the exercises that we are going to start doing must be done with 8 bits. Okay, so let's do it here. 1, 2, 3, 4, 5, 6, 7, 8. And in here we have the values of 1, 2, 4, 8, 16, 32, 64, 128. Okay, okay. So this is the process that I do. But okay, this is bigger than 8-bit, but it doesn't matter. I'm going to use it. So let me delete this. And I'm going to add another one, and this one is 256. Just for conversions, it doesn't matter the numbers. But with another types of exercises, we use always 8-bit numbers. Okay, so let's start doing this. So I'm going to start looking if any all those numbers we can subtract them from this number. So we are going to start with 256. So 375, we are going to subtract 256. So here we have 9, here we have 1, and here we have 1, and here we have 1. Now we cannot use this one, so here we are going to put 0. Now this one we can use it. So I'm going to put 1 and I'm going to make the subtraction. So here we have 64, here we have 5, here we have 5. Okay? We can use this one, so I'm going to put 1 and I'm going to make the subtraction. So here we have 23. Obviously, we can use this one. I'm going to do it like this. So this is 7. So we cannot use this one, but this one. So 7 subtract 4, 3. This one and this one. Okay? So if you notice here now, oh, okay, here. This is the binary number of 375. Now I'm going to separate all the 4 bits numbers. So 2, 3, 4, d d d d 1, 2, 3, 4, d d d d. And in this case, we are going to add 0, 0, 0. Why? Because we need to complete the 4 bits. Okay, so you are going to take every section and you are going to convert that section to hexadecimal number. So 0001, this one, all this one is 1. 0111, if I remember, that number is 7. And here we have the same 0111, so that means that is 7. Now, this number is pretty similar to the decimal numbers. So, to differentiate this number from decimal numbers, you must do this 177 base 16. Okay. Now, what if in these numbers you get a number greater than 9? So, for example, let's suppose I'm going to give you an example here. I'm going to use 0011 110 101 So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So this is 0. This is 15, but in hexadecimal, 15 is F. This one is 5, and this one is 13, but in hexadecimal numbers, 13 is D. So that means that all these number in hexadecimal is 0, F, D. Ready? Okay. It's pretty similar if you want to do it in the inverse way. It's pretty similar. So let me explain this. I'm going to convert from hexadecimal to decimal. So I'm going to do it with the number 2 and the number F. Okay. So the number 2 here is 1, 1, 0, 1. And the F is 1, 1, 1, 1. If you join them, you are going to have this number 0, 0, 1, 0, 1, 1, 1, 1. So you need to do this 1, 2, 4, 8, 16, 32. And here you already know what you suppose or what you have to do. So 1, 3, 7, 15. Okay, this is the number. Okay, 2F is equals to 47. Okay, this is base 16, this is base 10. Okay, okie dokie. So all this that I explained using my iPad is here. How to make the conversions and everything. Now, why the computers use hexadecimal? Why? For data representation. So imagine this. Now I'm going to delete all this. Imagine this. Let's suppose that you have this binary number. 1, 1, 0, 0, tin, 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 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0. That is too long. So can you repeat this number without any mistakes? Let's suppose that you are writing this, reading it from a paper or from a book, and you must write that number from that book to any piece of paper. Maybe you are going to do something like this. Let's suppose that you are doing this. Okay, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1. Oh, I made it wrong. So as much bigger the binary number is, you are going to make mistakes. Okay, so that is the reason that the computer represents those numbers using hexadecimal numbers. It's easier for us as human. Okay, so 1, 2, 3, 4. 1, 2, 3, 4, in, 1, 2, 3, 4, in, 1, 2, 3, 4, in, 1, 2, 3, 4, 1, 1, 2, 3, 4. Then you're going to make the conversion. So this one, if I remember, this is 6, this one is 7, this is 10, so that means that is A. This is 11, that means that is B. This is 13, so that means is D. And this one is 6. So that huge number is 6, 7, A, B, D, 6. So this number is easier than all these long binary number. Okay? So that is the reason that the computers uses hexadecimal. Okay? Okay, so look at compact representation, easier for humans to read, less error prone, and easy conversion. Okay, now where the hexadecimal is used. When you are using, so I cannot show you this here, but let me, okay. So look at here. In this part, we are in processors, okay? All these processors in this moment are in my RAM memory. Okay? So the Google Chrome, the ChatGPT. Why ChatGPT if my ChatGPT is closed? Oh man. Okay, doesn't matter. So all these are temporary files that are stored in my RAM memory. So the RAM memory is located in specific places. That means that in the RAM memory, you have locations, and every single location has an address, and that address is given using hexadecimal numbers. Okay, so if you are creating web pages, so possibly you are going to use la paleta de colores in HTML. So here you represent any single color using a hexadecimal number. Okay. If you want, remember this. When you are connected in a network, when you are connected in a network, you have those two identifications. One is the IP address and the other one is the MAC address. The MAC address uses hexadecimal numbers. Okay? And the other uses that we gave to the hexadecimal numbers is, for example, that you are playing any games or maybe your game crashes. So you are going to have a message error with a number of error. Okay. Okay. Binary addition and overflowing. Guys, here I have to apologize because I explained something wrong. Okay. But it's not a big deal, but you need to be careful. So remember that I told you that we always are going to work with 8 bits numbers in binary, right? So that means that I am going to have a number like this: 0, 1, 0, 1, 1, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. And I am going to add another number: 1, 0, 0, 1, 0, 1, 1, 0, 1. Okay? So that means that the result of this addition must be in another 8-bit number. So let's see. Here, 1 plus 1, we have 10. Here we have 1. Here we have 10. And look at here. 1 plus 1 plus 1 is not 10, is 11. What that means that here I'm going to put 1 and here I am going to put another 1. Okay, and 1 plus 1 is 10. 0 and 10. 1 plus 1 is 10. 0 and carry 1. 1 plus 1 is 0 and carry 1, 1. So if you notice here, we have 1, 2, 3, 4, 5, 6, 7, and 8 bits. So here, do we have an overflow? No, there is not an overflow. Why? Because you have, as a result of these 8 binary addition numbers, you have another 8-bit numbers. What if the number is like this one? Another color. I'm going to use 1 0 0 1 1 0 1 1 2 3 4 5 6 7 8, and I'm going to add this one. I'm going to do it here like this because I need to do it faster. So 1 1 0 1 0 1 0 1. If you notice, chin, 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 this is the bit number 9. Look at 1, 2, 3, 4, 5, 6, 7, 8, and 9. I told you that you need, yes, there is a overflow, and I told you that you are going to add the other zeros. No, that is a mistake. Okay? Why? Because you need to represent the addition in just 8-bit. So that means that you have a bit number 9 that is overflow, and that is an error. So that means that you are going to miss this bit, so the addition is going to be wrong. Okay, so overflow means that there is an error in our additions. Why an error? Because we are working with 8-bit numbers. If you get another bit in addition, that is wrong. Okay, so consider that, please. And I apologize because I know that I explained that wrong. Okay, so this is the rules for addition. So look at 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 10, and 1 plus 1 plus 1 is 11. That is what I explained here. Let me delete all this, and I'm going to explain once again. Doing this 0 0 0. Oh, sorry. Here we go. 0 1 1 1 0 1 1 1 10, and 1 1 1. Let me do it here. 1 1 1. We have 11. Why? Let me explain. No, 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 no. Okie dokie. 1 plus 1 is 0 and carry 1. And this 0 plus this one is 1. Then you have the other one here. Okay? That is the reason that 1 plus 1 plus 1, the result is 11. Okie dokie. Okie dokie. Let's continue. Here I am showing you, telling you about the mistake that I did. So this is the correction. You find it in this video, and you have it here in this presentation. So perform a logical binary shift on a positive 8-bit binary integer and understand the effect this has on the positive binary integer. And look at this, 8-bit binary numbers. So remember, we always in IGCSE are going to use, unless the exercise says something different, always we are going to use 8-bit binary numbers. So what is binary, logical binary shift? Okay. So we have, I thought that I delete everything, but not. Okay. Logical binary shift. Okay, so here we have two: left logical binary shift and right logical binary shift. What is that? It's just when you are moving the digits to the left or to the right in a binary number. But look at this. When you're talking about left logical shift, is the same when you got the binary number and you multiply, or you take that binary number times 2. And when we are talking about right logical shift, we are talking about that you are going to take the binary number and you are going to divide the number. Now this is percentage. And you are going to divide the number by 2. So let me show you this right here. I'm going to use, or I'm going to, yes, the sorry, left binary shift. I'm going to write one. So let me use 0, 0, 1, 1, 1, 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So remember that always we have those numbers here: 1, 2, 4, 8, 16, 32, 64, 128, and 256. 1, 2, 3, 4, 5, 6, 7, 8. Huh? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this one, okay. Ready, 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 ready. So let me try writing this better. So here I'm going to use 1, 1, 0, 1, 1, 1, 0, 0. This is the number. Okie dokie. So if we are going to make left binary shift, that means that you are going to start adding a 0 on the right part. And you are going to start moving the other numbers one place to the left. So that means that here I'm going to put 1, 1, 0, 1, 1, 1, 0. So if you notice, this one is moved here, 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 and this one, oh, is missed. Okay. Now, let's calculate those numbers. I'm going to use green. I'm going to calculate the decimal number here, and I'm going to calculate the decimal number here. So let me show you. So here we have 1, and this one we have 3. Why? Because I'm adding this with this. So 1, 3, 11, 27, and 27 in addition with 32, 59. So remember this number, 59. Now I'm going to do the same with the number below. So I'm going to use this one. So here we have 2, 6, 22, 54 and 64 and 54. Here we have 8, 10. Okay, so we have 118. And let me show you. I am going to multiply this by 2, and the answer is the same number. That is the reason that I explained to you that if you are using left logical shift is the same that taking the decimal number times 2. So this is the explanation. Now, what if I have this number? So here we have 1, 0, 1, 1, 0, 1, 1, 1. So I'm going to apply the logical shift, left logical shift. So I'm going to put 0, 1, 1, 1, 0, 1, 1, 0. And if you notice, this one is missed. So let's calculate the decimal numbers here. So this is 1, 3, 7, 23, 23, 55, and 55 in addition with 128. So here we have 13, here we have 8 and 1. Okay, so this number is 183. Now I am going to do the same here. So we have 2, 6, 14, 46, and 46. Here we have 10. So if you have 183 times 2, here we have, and is not the same number. So here, if you notice, this is a overflow. Why? Because this one increases the space. Remember that the zero on the left uh, doesn't matter on the left, but the one on the left has a value. So here we have an overflow, and remember the overflow is an error. Why is an error? Look at 266 is not the same number when we are doing the logical left shifting. Okay, now let me explain you the other logical shift, that is the right logical shift. This is pretty similar to the previous ones, just the difference is, let me show you. I'm going to use here 1, 0, 0, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and we have to do the same. I'm going to use 1, 2, 4, 8, 16, 32, 64, 128. The right logical shift is that you are going to add a 0 now on the left, and you are going to start moving all the numbers one place to the right. So 1, 0, 0, 0, 1, 0, 0, and this 0 is missed. Now let's do the calculations. Okay, so here we have 8, 136, right? This is a number 3. Ah, 36. Now let's calculate the other number. 468. This one is 68. And I'm going to take 136 and I'm going to divide this number by 2. Okay, so we have this. Now, if you notice, this number is equals to this number. That is the reason that if you do right logical shift is when you take the binary number and you divide that number by 2. Okay? But there is one way that you can have a possibly not an error, but let me show you. I'm going to use 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to do the same here. 1, 2, 4, 8, 16, 32, 64, 128. And I'm going to apply right logical shift. That means I'm going to put a 0 here and I'm going to move everything to the right. 1, 0, 0, 1, 0, 1, 1. And this one is missed. Now let's do the same process. Here we have 1, 3, 7, 23, and I'm going to add this. So here we have 10, we have 10, and we have 10. Okay, so this number is this one. And now I'm going to do the same with this one. 1, 3, 11, 75. So let's calculate this. I'm going to have 151 divided by 2. So here we have 7, 11. This says that 11, here I'm going to put 1, sorry, here I'm going to put 10. Why? Because this 5. And here we are going to have 1. So this reminder is missed. Okay, so here nothing happens because we have the same number, but the difference that is you have a reminder and that reminder is missed. Okay, so there is no problem here. Let's continue. I'm gonna try doing a little bit faster because it's too late and I have to sleep. Okay, let me see. The microphone is recording. Yes, the microphone is recording. I'm going to close this and I'm going to come here once again. Okay, here is the explanation of the logical right, left and right logical shift. Okay. Okay, the two complements representation of, guess what? 8-bit integers. So what is this? This is the way that you are going to convert any negative number to binary. Okay, so let's do it here quickly. Okay, I'm going to use the same the example that I have in the PowerPoint presentation. So if you're going to convert 23 to binary, if the number is positive, you don't have to do any change. 1, 2, 3, 4, 5, 6, 7, and 8. So here you have the same 1, 2, 4, 8, 16, 32, 64, and 228 in this case, okay? So as always, you here are going to put a 0, 0, 0, and now I'm going to take the number 23 and I'm going to subtract 16. Yeah, that means that here I have 7. That means that here I'm going to put 1. For the 8, I'm going to put 0. For the number 4, I am going to put 1. That means here that I have 3. For the number 2, I'm going to put 1. That means that we are going to subtract 2 from 3. And here we're going to put 1 because we can subtract 1 from 1. Okay? So this is the conversion of the number 23. Okay? So the original number is positive. Okay? So here we finish the activity. But what if the number is not positive but negative? So you have to do the same process. So you are going to calculate the binary of the positive part. But now you need to start doing something that is applying the two complements. So the complement one says, let me put it a little bit here. Complement number one. That complement says that you are going to use all the numbers in the binary that you got, and you are going to change its value with the inverse one. What that means that I'm going to take this one, and now it's going to be a 0. This one, 0. This one, 0. Now this 0 is a 1. This one, 0. This 0, sorry, 0. This 0, 1. This 0, 1, and this 0, 1. That is the complement 1. Now we have the complement 2. That says that you are going to add to this number the number 1. So 0, 0, 0, 0, 0, 0, 0, 1. And the result is 1, 0, 0, 1, 0, 1, 1, 1. Now this is the negative binary number of 23. So the most significant bit in this number is going to tell you if the number is positive or negative. For example, if we take this one, look at that the most significant bit is 0. That means that the number is positive 23. But in this one, the most significant bit is 1. That means that the number is negative. So let's try it. 1, 2, 4, 8, 16, 32, 64, 168 negative. And let's do the additions. So 168, we are going to add, oh, sorry, we are going to add 64. So here we have 4, here we have 0, 10. Okay. Now I'm going to subtract or to add 32. So here we have 2 and here we have 7. Negative. Now we are going to have negative 72. No, I did I did something wrong here. Okay, let me see. 168, and we are going to subtract 64. That is 4. That is 0. Let me Let me continue. But I think this is wrong. I'm doing something wrong here. 64, 32. I did something wrong here. Oh, yes. Yes, 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 yes. I'm going to delete this. The number is, oh man, 128 negative. Okay, so let's start over again. So 128 negative, we are going to add 64. So here we have 4, here we have 6 negative. Now we are going to subtract, to add to this one 32. Why? Because we have 1 here. Here we have 2, and here we have 3 negative. Now we are going to take 32 negative and we are going to add 8. That means here we have 24 negative. And to negative 24, we are going to add 1. So we have negative 23. Okay? So that's all. So remember, the complement number 1 says that after you do the conversion from the denary number to binary number, you are going to change all the binary numbers values by the inverse one. Then to that process, you are going to add 1, and that is your negative number. And that's all for this video, guys. So I think this video is shorter than the previous that I did, but I have my microphone stopped working. For that reason, all the video, okay, record my screen, but I didn't record my voice. So that is the reason that I had to record this video again. And that is the reason that I usually checks that this software is recording my voice. So thank you guys. So let's see you in a next video. Bye bye.